The people I don't see here today are Michael, DJ, James, and Clayton. Michael, okay. I want to start off by looking at the results we got from lab this week because I think it's kind of cool. So here is the raw data graphed out from lab. And you see that there is no labeling here, so I'll just put them. I didn't show all the way up. This is the hot water. The light blue is the cool water. The dark blue is the salt water. And this one here was just a probe in air. I put the probe in air there so we can, A, get an idea of how quickly the probe responds, as well as get a baseline for what was the actual temperature in there. And so I used this temperature here, which is about minus 72.5 degrees Celsius, as the temperature for comparison of what the temperature in the freezer was when we did this experiment. And honestly, I meant to include the hot going all the way up because one of the first things you should have noticed was that the slope for this hot water, get my closest to the color, was steeper initially than the slope for the cool water. It cooled more rapidly. And then we have the primary question that you were supposed to answer was, what freezes faster, hot water or cold water? So freezing is done when it leaves the 0 degrees. And so you look at that and you compare the aqua versus, or cyan versus the olive green, let's call it. And how do they compare? Which one leaves 0 degrees first? Just to make sure everybody's following along, which one left first of those two? I marked where the times where they left. The cool water. Yes. So which one freezes quicker, hot water or cold water?
Cold water.
Cold water, right. Now, another way we could have asked this is once you reach 0 degrees, which one took longer? So you could have gone from here to here and compared that to, compared that to from here to here. And they come out to be almost the same. According to my measurements, it was 2,300 seconds for the hot water and 2,200 seconds for the cold water. But given the uncertainty in determining when they actually leave 0 degrees and the fact that we know the mass has changed over time because the mass we measured after we were done with the experiment showed that the hot water had evaporated some, I'm willing to say that's a wash. They took the same time to actually go from being liquid water at 0 to solid water, i.e. ice, at 0. This is pictures showing what happens when they reached freezing. And the first thing you note here is something that we have not talked about. Let's just take the cyan line. That's the room temperature water, the cool water. What happens to the temperature at the outset of freezing?
It dips first.
It dips first. Does anybody know what it's called when it dips here? Right. This was super cooled. Super does not have an O. But cool does. It was super cooled. It was actually cooled below the freezing temperature. It's possible to do that. It's not stable. Any little bump or whatnot can make it then suddenly change quickly. And so what happens when that line goes back up is suddenly you had a lot of the water froze. So it was a much more rapid freezing for that little period because it had been super cooled. This also happens, well, it happens with any change of phase. So you can do the same thing with hot water. How many people have heard of the dangers of heating up water in a microwave? Only one. One in a shaky hand. Well, you can go search online. You'll find plenty of stories of people who put their water in their coffee mug, they put it in the microwave, and they meant to hit 1 minute, instead they hit 10 minutes. They come back, They take their water out of the microwave, and as they're taking it out, it blows up in their hand, and they get scalded terribly. That's happened to many people. I mean, many is not millions, but it's happened to
every
many
day.
people.
Lives are taken.
No, that's just a McDonald's. It's every day, actually. You guys know about the lawsuit with McDonald's. The lady was, by the way, severely burned with that thing. It wasn't like, oh, I'm uncomfortable. She was hospitalized. I think she might have had skin grafts. Anyway, so back to this. That can occur because you can superheat the water. You can get water, pure water should boil at 100 degrees. But you can get it up to, 105 degrees Celsius. And then if something jostles it, all of a sudden a huge amount of it boils at once. And so that's very bad. So what do you do in chemistry lab to avoid that? Okay, mixing it will work.
Boiling chip.
Yeah, you put a boiling chip. The boiling chip will trap little bubbles of air. And those little bubbles of air will act as nucleation points. They'll start the boiling when it reaches 100 degrees Celsius, and then everything will be fine. So there's a good reason to put those in there. We in physics just have really dirty glassware. That also covers the base. You probably noticed how dirty my glassware was. Next thing is the boiling or the freezing temperature. Freezing temperature for the cold water was 0 to the best of our measurement. For our hot water, it was a little bit below 0. Now, I said in class it's probably just a difference in the probe, but it also could have been because I boiled that water in a pretty dirty beaker, and it could have picked up some more calcium carbonate that was coated on the beaker, and so that impurity could have lowered its boiling temperature or its freezing temperature just a little. And if we look at the salt water, you see the salt water definitely had a reduced temperature before it started freezing. And then what in the world is going on there? As the salt water freezes, what's happening to the freezing temperature? It's going lower and lower. Why? Yes. Now, first of all, I didn't mix this very well, but what freezes is going to be pure water dropping out the salt. So what remains is saltier and saltier and saltier, and so it's depressing further and further for the freezing temperature. Now, a calculation based on this. From my analysis, the cooling rate going from 20 degrees to 10 degrees Celsius was exactly the same. I just used finding the slope of the data, selected a box going from 20 degrees Celsius to 10 degrees Celsius on each of the data sets, and I got exactly the same cooling rate. So given that cooling rate, change in temperature over change in time is equal to minus 0.0305 degrees Celsius per second, and that mass was equal to 65.35 grams, how quickly was heat being removed from the water? How can we go about calculating that? First step is I'm going to need an equation, right? And what equation do we have that relates the change in temperature to the heat? Yes. We have Q equals MC delta T. So I'm just going to divide both sides by delta T. And I have the heat per unit time. Whoops. That's a capital T for temperature. The heat per time is the mass times the specific heat of water multiplied by this rate of change for temperature. So I can put in my mass value, my specific heat, and notice I can do it in calories or joules. A joule is 4.186 calories, so either one's going to work. I'm going to choose to do calories because I can do that math mentally. Now, of course, I still can't do the last one in my head. So if we take that 65.35 grams times 1.00 calories per gram degree Celsius times minus, because it's removing, 0.0305 degrees Celsius per second, what do I get for the rate at which heat was being removed?
Negative 1.99.
Negative 1.99 calories per second. So that's how quickly heat was being removed from the water when it was at between 20 to 10 degrees Celsius. Now for my last question on this, for the first 100 seconds, a bigger range in time, a smaller range in time, the hot water cooled at this rate and the cold water cooled at this rate. And I should put a minus sign there to be consistent. The negatives are because it's cooling. The environment was at minus 72.7 degrees Celsius. So is this consistent with Newton's law of cooling? To answer that, you have to recall what Newton's law of cooling was. What was Newton's law of cooling in rough terms? The what? The rate of cooling is proportional to the difference in temperature. And so as we saw from what we just did, the rate of cooling is proportional to the rate of the temperature change. You can call it rate of cooling for both, one's temperature and one's heat. And so I should be able to say the change in temperature per time for the hot water divided by the change in temperature per time for the cold water should be equal to the temperature of the hot object minus temperature of the environment over temperature of the cold object minus temperature of the environment. If that's equal, then that would say Newton's law of cooling was correct. If you do these calculations, 0.0693 over 0.0412, what does that give you? Uh-oh. So calculators out now. This divided by this. Okay, and then if we do the difference in temperatures, that's going to be 54 plus 72 is 126.7, and 54 plus, or 17.7 plus 72.7 is 70. What is that ratio? So those are not equal to each other. So we don't exactly have it showing following Newton's law of cooling. That can be explained in numerous ways. We have things like air flowing over and maybe some conduction out. So it's not super surprising that it didn't exactly follow Newton's law of cooling. We know that's not equal, right? But it is in the vicinity. So just wanted to point out some of these things that you can glean from what we did in that lab experiment, which I think is totally fun. Of course, I think all of my physics is fun. Last class period, we talked about the three mechanisms for heat. What were the three mechanisms? Conduction, convection, and radiation. So the doer is designed to stop these. How do you stop conduction? Okay, I'm going to put lower area of contact because you can't contact once again. You can't make zero area of contact, but you can make it as small as possible. You can also lower the thermal conductivity. So glass is used because it's a fairly low thermal conductivity for a solid. The lowering the area of the thermal of contact is by making thin walls of the glass. So that's how we minimize the conduction. The last thing is make the path length that it has to conduct along. And so with the double wall, if I have something that's hot here, the heat would have to travel, well, that's going the wrong direction. It would have to travel like this to start heating up the water. It's a long distance it would have to travel. What about convection? How do you stop convection? Okay, you lower the flow of air. If you pull out all the air, then you're going to have no flow of air. So there's a vacuum between the surfaces, so there can be no convection between the surfaces. Radiation. How do you stop radiation? You what? No, you can. Remember my sweet blanket that people were taking pictures of me in?
Oh, yeah.
Okay, we need something that is either white or even better than white is reflective. And so in this case, it has the silver surface wall, so they're reflective.
For like chemotherapy or radiation, like to protect the other parts of your body?
Chemotherapy is not radiation, but when you're going through a cancer radiation treatment, the radiation might be something like protons or electrons or gamma waves. And so gamma waves are the same type of radiation as we're talking about here. The protons and electrons, we'll talk about that second semester. We'll talk about the medical treatments and radiation there. But let's put it to something that people are more familiar with, because most of us haven't had gamma knife surgery on our brains, which is the only place I know for using gamma radiation for treating cancer. But we have x-rays at the dentist all the time. I'm going to go in next week, might get x-rays. X-rays is a type of radiation. Radiation can be bad, especially if it is shorter wavelengths than visible light, like ultraviolet light. So you go out, there is a certain amount of ultraviolet light that gets through the atmosphere. That can be bad. And so when you're getting the x-rays at the dentist, they have you wear the lead vest because that will stop the radiation. Now that's absorbing it, not reflecting it. So it's using a different method of stopping the radiation. It's absorbing it before it gets to you rather than reflecting it off. But that is the same type of radiation. Yeah.
So I've always wondered that when we do go to the dentist and they make us put that thing on to protect ourselves, so then they're trying to get pictures of our face, you know, through X-rays or whatever. So that doesn't that harm our face? Like
Sure.
So what about people who have to get X-rays consistently? Like that's
It's bad. Same thing for airline pilots, right? Airline pilots are flying higher in the atmosphere, which means there's less atmosphere around them, which means they get more radiation. And we have become more safety conscious. When my mom was a kid, she loved going to the shoe store. Not to get shoes, but because they had a box for sizing your foot. You put your foot in and you press the button, and you see your foot. It was taking an x-ray of your foot, a radiogram, and you could see it. And so she was x-raying her feet, all the time. And then they realized, no, this is not good, but it's not super bad either. So we still get x-rays because the good far outweighs the potential bad. All right, let's get to some new material. We learned about the specific heat using the equation that Emily recalled for us. Come on, finger. Q equaled MC delta T. C there was the specific heat capacity, if you want to be all kinds of specific. Well, if we have a gas, we have some different variations that we can have on this. If we put heat into the gas, then it should have a temperature change. And for a gas, the internal energy is just going to be the result of the kinetic energy. So the total kinetic energy of a monatomic ideal gas. So now we're limiting ourselves to gases that have only one atom per molecule. That's helium, neon, argon, krypton, xenon, radon. I don't even know what Lu is. But we're limiting to only those here. We're talking about monatomic ideal gases. So for the monatomic ideal gas, the total kinetic energy is 3/2 nkt from what we've already learned with the kinetic theory of gases, right? We learned from the kinetic theory of gases that temperature related to the average kinetic energy. And I need to turn off the sound on my watch. That's not good at all. Go away. So using the ideal gas law, we can say that the total kinetic energy, which is equal to the total internal energy, we use U as our symbol in thermodynamics for the internal energy. Internal energy is equal to the translation kinetic energy, 3/2 capital NKT or 3/2 lowercase n RT. Remember, capital N, the number of molecules. Lowercase n, the number of moles. So those are equivalent equations. And so if we're going to talk about the heat, the energy that's transferred in or out, assuming that we have no work, then the heat will just be the change in internal energy, which will be the change in the average kinetic energy. So if you have constant volume, which means no work, then the heat is 3/2, and let's go with this one, 3/2 nR delta T. Now we talk about a specific heat for liquids and solids. We said the specific heat was the heat per unit mass per change in temperature. For gases, instead of per unit mass, we talk about per molecule or per mole. So since I put a box around the per mole equation, we will use that the heat is the number of moles times the constant volume, that's why there's a subscript of V, molar specific heat times the change in temperature. This is defining the molar specific heat, the constant volume molar specific heat, specifically. And just taking this equation right here and comparing it, I'm going to change colors because I have too much black. Taking this equation here and comparing it to the equation above, we can directly read that the C sub V in the lower equation is replaced by 3/2 R in the upper equation. So the molar specific heat at constant volume for a monatomic ideal gas should be 3/2 R. Now that is a pure theoretical number, assuming something's ideal. What makes something ideal again? For a gas, that is?
Massless.
Not actually no mass.
No interaction.
Okay, no interaction, and it's not massless, but you were thinking the right area. No volume.
No volume.
Those are the two things that make a gas ideal. Nothing has no volume. Nothing is completely non-interacting. But if you have high temperature, the amount of energy exchange when things come close is really small compared to the total energy. And so we can approximate that as being ideal, no interaction. If you have a low density, then the molecules are fairly far apart. And so the size of the molecule compared to their separation is such that we can treat them as having no size. So that's when we can treat things as ideal gases. So from this, we saw that the molar specific heat at constant volume is 3/2 nR, or 3/2 R. I talked about the equipartition theorem before. The fact that in physics, energy will be distributed equally among all of the available degrees of freedom, all of the different ways that you can store energy. And it's just going to put in 1/2 kT into each of those degrees of freedom. That 1/2 kT, if we look here, we had 3 degrees of freedom, and so we had 3R here. The 2 is from the 1/2, the half part. And so if we have more than 3 degrees of freedom, that molar specific heat at constant volume for an ideal gas, got to put these disclaimers on here so you don't try to apply it to air, is going to increase by 1/2 kT or 1/2 R, for every additional degree of freedom. And at this point, you're probably just sitting there saying, he keeps saying these degrees of freedom, and it means nothing to me, really. We talked about before the degree of freedom, ways of storing energy, and I said that for the monatomic ideal gas, even though kinetic energy is a scalar, we say that it can store kinetic energy, or it can have kinetic energy related to its momentum in the x direction, its momentum in the y direction, and its momentum in the z direction. So we have 3 degrees of freedom for monatomic ideal gas. But if you have a diatomic molecule, then you're going to have more degrees of freedom, because a diatomic molecule can rotate. It can rotate about, if it's diatomic, it's a straight line. If it rotates around its symmetry axis, because all of the mass is essentially on the axis, what's the moment of inertia if all the mass is on the axis, has a radius of 0? 0. Hence, your kinetic energy, 1/2 I omega squared. If I is 0, 1/2 I omega squared is 0. So you can't have any energy in the first one. This case here has no energy, because I is equal to 0, because the mass is all on the axis. But you can still have rotation about the other 2 axes that are perpendicular to that. And so rotation adds 2 degrees of freedom. According to the equipartition theorem, how is that going to change the molar specific heat of an ideal gas if it can rotate? Goes from 3/2 R to, how many degrees of freedom did I add? 2. Each one adds 1/2 R. So it should go from 3/2 R to 5/2 R. Now, that's not the only new degrees of freedom that can occur if you go to a diatomic molecule. What else? You guys have probably studied this if you've taken organic chemistry. What else happens in a diatomic molecule that has energy associated with it? You treat them like they're 2 masses held together by a spring. Remember that?
So sloshing of electrons.
They can, the molecules can vibrate. They can go in and out. And that actually adds 2 additional degrees of freedom. One for the kinetic energy in the vibration, and one for the potential energy stored by the spring. And so you have a total of 7 degrees of freedom available in a diatomic ideal gas. That means that you would have 7/2 R for the constant volume molar specific heat for a diatomic ideal gas. Let's look at reality. Here's reality. At low temperatures, a diatomic ideal gas has a molar specific heat of 3/2 R. That's the same as a monatomic ideal gas. And now any logical person should say, he's lying, there's something wrong with the theory. What's wrong with the theory is quantum mechanics. Quantum mechanics says that you just can't have something rotate at any old rate. I know when James was up here sitting and spinning, he could speed up and slow down freely. But quantum mechanics says there are only certain speeds he can have for his rotation. He couldn't just continuously change speed. And there's a minimum speed. And if the temperature is lower than the temperature required for 1/2 kT to equal that minimum energy, no energy will go into rotation. So at really low temperature, they can't rotate. Is that bizarre? They can move around, but they can't rotate. But that's what quantum mechanics says. So that's why it's 3/2 R at really low temperature. When you get up into a room temperature situation, you get a high enough temperature that they can rotate, but still not enough energy to excite the vibrations. And so you have an additional 2 degrees of freedom, hence going up from 3/2 R to 5/2 R. And then if you get to high temperature, then it can start vibrating as well, and it goes up to 7/2 R. So the quantum physics, yet you have to pay attention to it at this point because it's a real life difference in your measurements. If you just ignore it like we've done up to here, you'll say my physics theory does not match reality. Here are some numbers for different gases. So here are monatomic gases, ideal gases that have only one atom per molecule. And you see the actual value for C sub V is very close to the expected 3/2 R. Now these are at 25 degrees Celsius. It makes a difference when you go beyond monatomic. So for the diatomics here, we have hydrogen, nitrogen, and oxygen. You wonder why did they choose those? What is air? Air is 79% nitrogen, 21% oxygen. So we've got the ones that are predominant in air, plus hydrogen because, well, we had to have something that agreed with our theory. Actually, the nitrogen and hydrogen both agree with the theory, pretty much. The oxygen, though, is a little bit high. Not much, but a little bit. And then if you get to polyatomic molecules, polyatomics are not linear anymore. So they are going to have 3 degrees of rotational freedom, not 2 degrees. And so you should have something close to, you would expect, 6/2 or 3R. Instead, you see it's closer to 7/2. Why the 7/2? I believe you have just a little bit of vibration or something in there as well. You can see when we look here that when you're transitioning between temperatures, you have a little bit of addition that occurs. And now we're ready to start what I really wanted to cover today, thermodynamics. All of that stuff was reasonably theoretical. Yes, you're going to probably have to do some calculations with Q equals NC sub V delta T. No different than what you did with Q equals MC delta T, really, except for you're replacing mass with the number of moles. This here is what's called a hero's engine, named for hero of, I think he's Alexandria. It seems like all these guys are from Alexandria. The first known heat engine. Heat engines are things that are designed to allow us to transfer energy from thermodynamic energy, thermal energy, something's hot, into mechanical energy, the useful kind of energy. Remember, we talked about mechanical energy. We had the kinetic energy, energy in motion, and we had potential energy, energy associated with configuration. And those were the energies that we can freely manipulate. Thermal energy is a microscopic form of kinetic energy, but we can't freely exchange it. And so a heat engine is designed to take energy from this hard-to-access thermal realm and convert it into mechanical energy. So the hero engine, as shown here, it's basically the same as having your little teapot. You have a fire down here, and then this basin is filled with water. So you heat up the water. What happens to the water? It changes phase and becomes steam. And the hot steam expands, and because it expands, it increases the pressure. You have atmospheric pressure outside, high pressure inside. These pipes just convey the high pressure gas into this bowl, and then the high pressure gas comes out of these little jets that are facing opposite directions, so it goes around a circle. Goes around a circle as the air rushes from the higher pressure area to the lower pressure area. So that's a simple hero engine. If you ever decide to read Richard Feynman's book, you'll see that when he was a freshman at MIT, he was very curious about this. Not that the Hero engine works, but what happens if you try to do it in reverse? If you try to suck the air in. And so he made friends with guys in the glass shop, and he went and he made one of the, well, something like the working part of the Hero engine, but connected it to vacuum to suck air in. It turns out without a lot of analysis, he just hadn't thought it through, you would recognize that it's not going to work if you suck it in. Because what actually makes that thing move? I talked about pressure, but it's really a lot more like a rocket. You had the steam was initially at rest. It comes out going in one direction. So you had a change in momentum for that steam. So what has to happen to the rest of the thing to compensate for the change in momentum? If I start with this ball in my hand and I throw it like that, what happens to my body to compensate for the change in momentum of the ball? It's going to recoil. It's going to go the opposite direction. That's how the Hero engine works. Well, with Feynman, he reversed it so he was sucking air in. You started with still air out here. You suck the air in and it goes into this hose. You essentially go from still air to still air. There's no net change in momentum, so no real action. But he was frustrated. So he lowered the vacuum as low as he could until all of his glass imploded. Glass went flying across the workshop, and he was banned from the glass shop after that. So that is a useful type of engine. What's another useful heat engine that you might interact with? A what? Yeah, a car engine. Car engines are examples of heat engines. So they're an example that we will look at to see how a heat engine can really be useful. Steam engines are easier to show on paper, but car engines are ones you're much more commonly using. Now we have to talk about laws of thermodynamics. We already talked about the 0th law. And in fact, I named all of them when I named the 0th law. The 0th law said if object A is in thermal contact or thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then object A is in thermal equilibrium with object C, which is really mealy-mouthed way to say if temperature A equals temperature B and temperature B equals temperature C, then temperature A equals temperature C. Which seems so obvious that there would be no possible reason to name that as a law until physicists really got a better understanding of what temperature was and realized that temperature was much more sophisticated than what they thought and needed to be stated. So it got shoved in as the 0th. So the first law of thermodynamics is the one that was thought to be the most fundamental law. And it says energy cannot be created or destroyed. You can't create energy, you can't destroy energy. Hence, by definition, you can't have an energy shortage, right? Because you can't create or destroy it. You always have the same amount of energy. When we talk about energy shortage, what we really mean is the shortage of material that we can efficiently convert the energy from the form it's in into mechanical energy that we can use. That's what we mean in practical terms when people say we have an energy shortage. Because you can't create or destroy it. You can convert it from one type to another. So the first law of thermodynamics is usually summarized in an equation. So here's that equation. Recall from a few minutes ago, U is the symbol we use for the internal energy, also known as the thermal energy. So delta U, the change in internal energy, is equal to Q minus W. Q, we've just been using Q a lot. What did Q stand for? Okay, well, it was heat, specifically. So Q is heat. So the change in internal energy is equal to heat, and then we have to add a word to modify heat. It's the heat added to the system, which is what DJ had said. So if heat goes into the system, the internal energy should go up. Just like if money goes into my bank account, the balance should go up. You can think of this just like a bank account. So Q is money added to my bank. Delta U is the change in the balance. And then we have W. W is work. But then we once again have to modify it. It's the work done by the system. So that's energy going out. That's why there's a minus sign. So with my money analogy, U is the balance of my bank account. Q is money being deposited into my bank account. And W is purchases I make. So the change in the balance of my bank account is equal to the deposits minus the purchases. That's the effectiveness of this equation. The change in internal energy is the heat added minus the work done by the system. So it's important. I'm going to have a couple questions I'm going to ask you to answer in a minute. That you remember, Q in this equation is heat added to the system. W in this equation is work done by the system. There are textbooks that will say W is work done on the system. If the textbook uses W as work done on the system, how is that going to change the equation for the first law of thermodynamics? Change it from done by to on. What's that changing? Yeah, it's changing the direction of the energy flow, so it changes to a plus sign. So it's really important to internalize and understand what this equation means because you'll see it different ways. Going back. What variables does the first law of thermodynamics relate? Okay, this isn't back, but I'm going to use it to go back. What were the three variables in that first law we just saw?
Or just
I thought you said C. Maybe I misheard
I thought
you.
you meant like the beginning.
Yeah. It was change in internal energy is Q minus W. But these here are very important. Does anybody remember what those are? This is the thing going back. These are the variables in the ideal gas law, otherwise known as the variables of state.
When you talk about first law, is that pertaining to an open and closed system?
That's pertaining to any system, yes. That's universal. So these variables of state, if you know all of those variables, it tells you exactly what state your system is in. Those are what you need. Now, if you're in chemistry, you add another thing, you add the chemical potential. But in physics, we just ignore chemical reactions. We don't have to worry about the chemical potential then. And these other ones, well, we're there to be distractors. Now the two questions about directionality. What is the correct definition of Q in the first law of thermodynamics? And everybody does this definition the same. Q was which one? It's heat added. You could use heat removed, but thankfully no one does. What's wrong with C here? Nothing contains heat. Heat is a transfer of energy. You can't contain the transfer. You have internal energy. When internal energy goes out, then you had heat flowing out, but you don't contain heat. Now, as used by the textbook, what did W stand for in the first law of thermodynamics? Done by the system. And once again, work is again an energy transport mechanism. You can't contain work. This is just some little numerical problems. If you have a system and you have 40 joules comes in and 25 joules goes out, and you have, notice the work in is -4 for it coming in, and 10 joules out, you can use the first law of thermodynamics to determine how the total internal energy is changed. So without paying attention to the specific equation we had, I can just look at this and say, I added 40, I subtracted 25, I added -4 and subtracted +10. Well, if you take that in total, the total amount of energy that came in was 44 joules. The total amount that went out, I'm just looking at the arrows to determine the direction. Total amount that went out was 35. 44 in, 35 out. It had a net increase of 9 joules. That's what the first law is all about, is being able to do that balance of energy. Does the first law of thermodynamics apply to you? We already had the question. Yes, it applies to any system. Applies to you, it applies to the flower, so on. When we get to the second law, which we won't today, we'll actually touch on some ideas that have to do with origins, because people will use the second law as argument origins, and I want to make sure we understand that. Getting to the actual heat engine. We saw Hero's engine. Using the first law of thermodynamics, we can say that for a heat engine to run and continue to run, the internal energy has to remain constant. This is pretty simple if you think about it. Let's say you have a car engine. What happens to the car engine if every time you go through one cycle of the car engine, the internal energy increases? What does that mean to the engine? What happens to material when the average energy of the molecules goes up? Temperature increases. So if our car engine, if we have the internal energy goes up every cycle, what's happening to the engine temperature? It's getting hotter. Now we do want that to happen for the first 5 minutes or so until it reaches temperature. But if it's doing that, what would happen to the car engine? It would keep getting hotter until it melts or something bad happens. So in order for the car engine to continue to run, continue to operate, you have to, when you get to the operating range, have the change in internal energy per cycle is 0. You're going to have energy go up and down in the middle of the cycle, but it needs to come back to where it started. And the reverse is also true. If it lost energy for every cycle, what would eventually happen? It'd get down to absolute 0, and then you have the third law of thermodynamics. Nothing can reach absolute 0. So in order for an engine to keep running, you have to have the change in internal energy for every cycle is 0. Which means that since delta U is equal to Q minus W equals 0 for a cycle, then the heat added must equal the work done by the system. So you have a balance between the heat added and the work done by the system. So for a heat engine, this picture here, whoops, let's not worry about zooming if it's not going to zoom right. This picture is showing, now it's zoomed, is showing a typical steam engine. You have water, you have a pump that moves water, and of course I can't draw when it's zoomed, a pump that moves water across to the boiler. And that boiler, you have a burning flame, so you have heat going in. So heat goes into the boiler, and we know that the boiler then is going to have water that boils, hence the term boiling. The hot water expands, and it is going to push on something. In this case, it's going to push on a piston. So if I have a force on a surface and it moves, what do we call that? Force and motion is work. And so that's going to do work on something. And so that's the work out. When you're done with the cycle, you're not going to have cold water. You're still going to have water in an elevated temperature. It's just not as high as it was at its high temperature. So you're also going to have some heat that flows out. So the heat added is actually the Q in minus the Q out, because heat flows in and heat flows out. So using the first law of thermodynamics, the heat in minus heat out is equal to the work done by the engine. This brings us to something disappointing. You can never, ever 100% convert thermal energy into work, mechanical energy. The reason you can't is you're always going to have that exhausted heat. It's never going to come out at absolute zero. If you could make your temperature cold absolute zero, you would reach ideal conversion. But the third law says you can't. So you can never perfectly efficiently convert heat into work. You can perfectly efficiently convert work into heat, just like this, right? You're converting the work into heat. Very efficient. You can buy yourself a space heater for your dorm room. Dr. Rose used to have an office next to me. I controlled the thermostat. Dr. Rose violated all kinds of fire safety laws, and he got a space heater for his office.
Necessary.
That space heater is 100% efficient, pretty much, in converting electrical energy into heat. But nothing can be 100% going the other way. Okay, we're out of time. Have a happy Sabbath.